You run a fund and you have to sell a large position before the closing bell. You could dump it all at once, trickle it out slowly, or anything in between. Each choice is a whole curve, your inventory falling from full to zero over time. And each curve carries a cost. Trade too fast and you crush the price against yourself. Too slow and you ride the risk of the market drifting away. The dump it all path pays a fortune in market impact. The slow trickle pays in risk, exposed to every twitch of the price for the whole afternoon. And somewhere between those two extremes lies the cheapest path of all. Look at them. Every curve scores a different total cost. So here is the real question. Not which number is smallest, but which whole curve is cheapest. We are not optimizing a number, we are optimizing a function. A rule that takes an entire curve and hands back a single number has a name, a functional. And by the end of this video, one equation will pick the best curve out of infinitely many. A function takes a number and hands you back a number. Turn the dial, read the output. A functional is hungrier. You feed it a whole curve and it hands back a single number. Here's the machine. J of x integrates g, which depends on the path x of t, its slope x dot, and the clock t, from the start time t naught to the final time t minus f. Endpoints, the curve, the clock. That's all g ever sees. A taller curve means more area underneath and a bigger number out. In trading, that curve is a price path and the number is what your execution costs come to. One whole curve in, one number out. That is a functional. Here's a fair question. Scale the whole curve up twice the height. Does its score just double? It depends on the score, the plane area underneath. Double the curve and you double the area. That's linear. But the squared score, the area under x squared, double the curve and you get 4 times as much because 2x squared is 4x squared. Same input, scale the same way, two different answers. That clean property is called linearity. Scale the input and the output scales the same. Area passes, squared fails. And this is the distinction that bites in markets. Because the cost that hurts, market impact, is the squared kind. Trade twice as fast and you pay 4 times the impact. Impact is an integral of rate squared. Non-linear, just like the integral of x squared. Two numbers are easy to compare. The gap between them on the number line tells them apart. But a trajectory is not a number, it is a whole shape. So how big is a curve? Sweep along it and watch its height. The tallest it ever gets in absolute value, anywhere from t0 to tf, is its size. That is the norm, the peak norm, the high water mark of the whole path. Now when our two curves close, draw a tube of half width epsilon around the first curve. A neighbor is close exactly when it stays inside that tube, never straying more than epsilon, everywhere at once. The widest vertical gap between them is the norm of their difference, and close means that gap is less than epsilon. And here's the trade. Picture two execution schedules, two plans for unwinding your inventory by the close. They are close when they share one epsilon tube, when at no instant do they differ by more than epsilon shares. Now the key move. Take a curve and nudge it. Add a small wiggle in orange. We call that wiggle the variation, delta x. The bent curve is a neighbor. How much does the cost change? Write the new cost minus the old. That's the increment, delta j. Work it out for a simple squared cost and two pieces appear. One is proportional to the wiggle, first order. The other is proportional to the wiggle squared, second order. Here's the crucial fact. Make the wiggle 10 times smaller and the first order piece shrinks 10 times, but the squared piece shrinks 100 times. For a tiny wiggle, the squared part all but vanishes and only the first order piece survives. That split, first order versus second, is the seed of everything that follows. Last time, we split the change in cost into a clean first order part and a smaller squared leftover. Let's build that first part from a picture you can see. Take a function of two inputs, the area of a rectangle, width q1 by height q2. Push just the first input. Stretch the width by delta q1, holding the other side. And the area grows by one thin strip. That strip is a rate, how fast the area grows when only this input moves, times the amount you pushed. And that rate is the partial derivative. Now the other input alone, a second strip, its own rate times its own nudge. Push both and the strips simply add. They sit in different places. The only overlap is this tiny corner, small times small, second order, so we drop it. Two inputs, two strips. More inputs, more strips. You can't help but write a sum. The differential df is the sum over every input of its rate times its nudge. Now lift that from a point up to a whole curve. The nudge becomes the orange wiggle, delta x, and the linear part of the change is the variation, delta j. So delta j is to the increment as the differential df is to the change delta f. The variation is just the differential lifted to whole functions. And in trading, nudge your unwind schedule a little and that slope is the marginal cost you act on. So when is a curve the best one? Think of a ball at the bottom of a valley. Nudge it in any direction and it doesn't roll downhill. At the lowest point, every direction is flat. The same must hold for our best curve. Wiggle it any way you like, and to first order, the cost cannot drop. So the variation of j must be 0 for every admissible wiggle. That is the fundamental theorem. Why exactly 0? Suppose it weren't. Suppose some wiggle lowered the cost. Then the opposite wiggle would raise it, which means the curve had a cheaper neighbor on the other side. It wasn't the best after all. The only way out is 0. In trading terms, at the optimal schedule, no first order reshuffle. Selling a little earlier or later can lower your cost. If one could, you weren't optimal. Before we derive anything, let's decode the one piece that trips everybody up, partial g by partial x times delta x. These two pieces aren't the same kind of thing at all. Partial g by partial x is a rate, one number you read off the cost. It answers a single question. If I lift the path a little higher, holding the slope and the clock fixed, how fast does the cost change? Dollars of cost per share of height. You don't choose it. The shape of the cost hands it to you. Delta x is a completely different animal, an amount, the number of shares you chose to lift by. One is a rate you read off, the other is an amount you picked. Now, because they're stacked like a fraction, the I wants to cancel that x against the delta x. Don't. A rate and an amount can't cancel. There's nothing matching to divide out. And the x underneath isn't a number at all. It's just a label, naming which knob you turned. So what do you do with a rate and an amount? You multiply. You already trust this from ordinary calculus. Rise equals slope times step. And nobody ever cancels the x in that. The units prove it. Dollars per share times shares is dollars, a real change in cost. The shares cancel, the symbols never do. Now the second knob, the slope, x dot, tells the very same story. Partial g by partial x dot is again a rate. Delta x dot is again an amount. So again you multiply, never cancel. But the slope knob carries one new twist. You don't get to choose delta x dot. Watch the chain. Lift one bead by delta x and the two links into it are forced to tilt. The slope changes whether you like it or not. So delta x dot is locked to delta x. It's just the time derivative of delta x. One push, two channels. That single lift changes the cost two ways at once, directly through the height and through the slope twist it forced. Add the two channels and you have the whole change in g, rate times amount for the height plus rate times amount for the slope. So keep 3 marks straight. Partial d is a rate of g. Delta is an amount you chose, or one your choice forced. And d by dt is a rate in time, the engine that turns delta x into delta x dot. A rate is never an amount, which is exactly why they multiply and never cancel. That delta symbol does double duty, so here's the deeper reason for it. An ordinary function like g eats a few numbers, height, slope, clock, and hands back a number. To wiggle one, you use partial d. But j, the cost of the whole schedule, eats a whole curve and returns one number. You can't write partial j by partial x because j depends on the entire shape of the path, not any single number. So bending a whole curve needs its own symbol. That's delta. Delta x bends the path a little. Delta j is how the total cost responds. And the two connect. You build delta j by adding up all those little rate times amount pieces along the path. One last pair. The increment, capital delta j, is the true change in cost when you bend the curve, and it can be curvy. The variation, little delta j, is just its straight line part, the first order prediction. Shrink the wiggle by 10 and delta j shrinks by 10, but the leftover shrinks by 100. So for a tiny wiggle, the straight line is the whole story. Keep those three ideas, and every line of the derivation that follows reads like plain arithmetic. We have the fundamental theorem. At the best curve, the variation of j is 0 for every wiggle you could draw. But 0 for every wiggle is still a statement about an integral. We want something far sharper, an equation the curve must obey at every single instant. Here's the move. Picture the path as a chain of beads pinned at both ends. It starts at x0 and finishes at xf, both fixed. Grab one bead and lift it by a tiny wiggle, delta x. How much did the cost change? Write the increment, the cost of the wiggled path minus the cost of the original, as one integral of the wiggled g minus g. Now zoom in on that lifted bead because two things changed at once. The bead now sits a little higher, and lifting it bent the two links into it, so the slope changed too. So g is being evaluated at a nudged height and a nudged slope. Expand it. A first order Taylor expansion in both. You get the original g plus the sensitivity to height, partial g by partial x, times the height wiggle delta x, plus the sensitivity to slope, partial g by partial x dot, times the slope wiggle delta x dot. There's a leftover, a term in delta x squared and smaller. But we already saw that for a tiny wiggle, the squared part is vanishingly small. Drop it. Subtract the original g, and the increment collapses to the first variation, the integral of partial g by partial x times delta x, plus partial g by partial x dot times delta x dot. Two clean terms, one for height, one for slope. But here's the snag. That second term doesn't ride the bead wiggle, delta x. It rides the slope wiggle, delta x dot. And delta x dot is just the time derivative of the bump, the up then down twist the lift created. Our two terms are multiplying two different things. Before we can conclude anything, we need them both to multiply the same delta x. That is the job of the next step. So we have two terms, one multiplying the bead wiggle delta x, the other multiplying the slope wiggle delta x dot. And we need both to multiply the same delta x. The tool is integration by parts, and the cleanest way to see it is the product rule. Watch what the time derivative does to a product. The slope cost, partial g by partial x dot, times the wiggle delta x. The d by dt of that product equals the rate of change of the slope cost times delta x plus the slope cost times the d by dt of delta x. And that very last piece is exactly our awkward term, partial g by partial x dot times delta x dot. So rearrange to isolate it. The awkward term equals the total derivative of the product minus the rate of change of the slope cost times delta x. Now integrate across the whole path. The total derivative piece integrates to just its endpoint values. That's the boundary bracket, partial g by partial x dot times delta x, evaluated at the two ends. In effect, the d by dt has hopped off the wiggle and landed on the slope cost. Put it all together and the first variation becomes a boundary bracket at the endpoints plus a single clean integral of partial g by partial x minus d by dt of partial g by partial x dot, all multiplying the same delta x. Now collect the gifts. Remember, the ends are pinned. The wiggle is 0 there, so the boundary bracket simply dies. What's left is the integral of one bracket times an arbitrary wiggle, and it must vanish for every wiggle we could possibly draw. Here's why that pins the bracket to 0. Suppose the bracket were positive at some instant. Then just choose a wiggle that's a small positive bump right there and 0 elsewhere. The integral would come out positive, not 0. Contradiction. The same trap springs if the bracket were negative. And we can slide that bump anywhere along the path, so no instant escapes. The only way the integral can stay 0 against every wiggle is if the bracket itself is 0 at every single point. That surviving bracket, partial g by partial x minus d by dt of partial g by partial x dot equal to 0, is the whole game. So here it is. Out of infinitely many paths from start to finish, the cheapest one is pinned down by a single local condition. Look at what that surviving bracket is really saying. Lifting a bead set off two effects, and now they sit side by side, both riding the same wiggle. One is the direct pull of height, partial g by partial x, how much the cost cares that the bead moved up. The other is the propagated pull of slope, d by dt of partial g by partial x dot, how much the cost cares that the links bent, carried along the path by that time derivative. On the very best path, the cost can't fall for any wiggle at all. So at every single bead, these two pulls must exactly cancel. Watch them snap into balance all along the chain. That balance, holding at every instant, is the Euler equation, partial g by partial x minus d by dt of partial g by partial x dot equals 0. It isn't a formula to memorize, it's a statement of equilibrium. At every moment, the direct cost of being where you are exactly cancels the cost your motion passes downstream. Underneath, it's a second order differential equation for the best path, fixed at both ends. But the meaning is the balance. Now the payoff. That chain of beads is your inventory as you unwind a position. Full at the open, 0 by the close. Lifting a bead means holding a little more, a little longer. One pull is the risk of holding inventory, exposed to every twitch of the market. The other is the impact of trading faster to get out. The Euler equation says that on the optimal schedule, at every instant, the marginal risk of waiting exactly balances the marginal cost of rushing. Solve that balance, and the path it carves is the Armgren-Kris curve, a smooth cinch glide down to 0. The rule for trading optimally is, quite literally, an Euler equation. Let's turn the crank on a real example. Take g equals x dot squared minus x squared. The Euler equation just needs two partials. With respect to x, that's minus 2x. With respect to x dot, 2x dot. Drop them into the slots and out falls x double dot plus x equals 0, the equation of a sine wave. Fit the endpoints and the extremal is exactly sine t, rising from 0 to 1 over a quarter period. But is it really a minimum? Add any neighbor, sine t plus a little wiggle, and recompute the cost. It comes out as the optimal cost plus 3 pi over 4 times alpha squared, a strictly positive surcharge. Every neighbor costs strictly more. The sine curve doesn't just satisfy the equation, it wins. Go back to that boundary term we threw away. We dropped it because both endpoints were pinned. But what if the final value is free? You don't dictate where the curve ends. Then the wiggle at the final time is no longer 0. And if that wiggle is free, the only way the boundary term can vanish is for the other factor to die. The partial of g with respect to x dot at the final time equals 0. That is the natural boundary condition. The problem chooses its own endpoint. Think about what that means. When both ends are pinned, you are imposing the answer at the boundary. When an end is free, the mathematics fills it in for you, finding the endpoint that makes the cost as small as it can be. For the shortest path to a vertical finish line, the curve must arrive perfectly flat, meeting the line at a right angle. Any steeper approach is a longer path. In trading, this is soft liquidation. If you don't force your inventory all the way to exactly 0 by the bell, the natural condition picks on its own the terminal inventory that minimizes your total cost. Now free the final time instead. The value is fixed, but you decide when to stop. The variation picks up an extra piece for the moving deadline, and setting it to 0 gives a new condition. G minus x dot times the partial of g with respect to x dot evaluated at the final time equals 0. For the worked example, the extremal is a parabola, and the condition pins the finishing time at 5. The same principle that bends the curve also tells you when to quit. In trading, that is the optimal horizon, not just how to unwind, but when to be done. Finally, free both ends. The endpoint can slide and the time can slide, so the general variation now carries two loose pieces. If the two are unrelated, each must vanish on its own. But the richer case is a moving target. The endpoint has to land somewhere on a given line. Then the two wiggles are tied together, and forcing the variation to 0 gives the transversality condition, a single equation linking where the path ends to how fast the target itself is moving. Take Kirk's example. The target line is theta equals minus 5t plus 15. Solve the Euler equation together with transversality, and the extremal is x equals t over 5, meeting the line at time 75 over 26. And look at how they meet. The slope of the path times the slope of the target is 1/5 times minus 5, exactly minus 1. The curve crosses its target at a perfect right angle. Transversality is just perpendicularity in disguise. In trading, this is the full problem at last. Choose the path, the stopping level, and the horizon all at once. Look how far one idea carried us. A functional, a whole curve scored by a single number, a variation, the nudge, the demand that at the best curve, the first order change vanish for every nudge. One integration by parts, and that demand became the Euler equation, the balance every optimal path must hold at every instant. Free an endpoint and a natural boundary condition appears. Free the final time and a stopping rule appears. Free both and transversality tells you to meet the target at a right angle. And every one of these had a trading twin, the optimal execution schedule, when to stop unwinding, the horizon itself. In part 2, the single curve becomes a vector, corners become allowed, constraints enter, and these conditions grow an extra set of variables called co-states, shadow prices on the dynamics. The calculus of variations becomes Pontryagin's maximum principle, the language of optimal control. See you there.